Okay, now already have pre-written so that we can, let me summarize. So first we'll start with let me bring the pointer. Okay, now let's do one thing. Let me start like this. So the chapter name is the wave optics. Fine. So and the Huygens wave theory is what we are going to discuss. So in the year 1678, the Dutch scientist, so like a Huygens, so we can call it Sir Huygens. What happened? He has proposed the wave nature, and in the 1675, the Newton proposed the rectilinear propagation of light. Maybe for another 200 years, nobody could not understand this wave nature. Only in the Young's what happened to demonstrate the wave nature, he took help of this Huygens wave theory. Then what happened? This has become so popular. Till then, what you can say, like, it was like a neglected part. The people could not understand what actually the Huygens wave theory is, because the total the ray optics already what we have studied. So there what happened, I think we discussed the most of the concepts with the help of the rectilinear propagation of light. That one. So let's begin one. So first I'll start with the wavefront concept. So what do you mean by a wavefront? It's a plane in which all particles will have a same phase. The wavefront can be spherical. So due to a point source, the wavefront will be a spherical one. So these are the wavefronts. Then for if the source is far away, then the wavefront will be a plane wavefront. So it can be like this. The wavefront will be spherical, can be cylindrical. So any of the things. So different waveforms. So once again, I'll put it. So the plane wavefront will be like this. The spherical wavefront will be like this. The cylindrical wavefronts will be like this. These are the like a wavefronts what happen usually we encounter in our discussion. So once again, I'll put it, it's a plane in which all particles will have a same phase. I think already the idea of phase you have encountered in the SHM and also in the waves and so on. What do you mean by phase? What do you mean by phase? It will give the instantaneous position of a particle. What is a phase? It will give the instantaneous position of a particle. So at a given instant, if all particles are having same phase, that particular plane, what happened, I can call it as a wavefront. And the wavefront can be of shape spherical, cylindrical, or plane wavefront. Hmm? Okay, fine. After this, now we'll proceed further to the coherent sources. What do you mean by coherent sources? Two sources of, let me introduce to the idea of the coherent sources. Two sources of same frequency with phase difference remaining constant with the time. They're said to be coherent. I'm asking you to look at this part of the content. Coherent sources. Two sources of same frequency with phase difference remaining constant with the time. The sources are said to be coherent. Example, I took the sine wave. What is the phase of this? Zero. I took the cosine wave. What is the phase difference between them? Will be 90 degrees. And that phase difference will remain constant at any time. So with this, what we can see. So they're said to be coherent. Phase difference can be zero. Altogether, the phase difference should remain constant with the time. They're said to be coherent. What about the incoherent sources? Two sources of same frequency with phase difference varying with the time, or two sources of different frequencies, they are said to be incoherent. So if you look at the source one, it is having a frequency f1. What about the source two? The source two is having frequency, which is having higher frequency, the waves emitted by the source two. This is f2, this is f1. So now what is the phase difference between them? The frequencies are different and the phase difference will vary continuously with the time. So the two sources of different frequency must be incoherent. What about this? So they are incoherent. You can see the phase difference is varying with the time. So definitely what you can say that these two are also incoherent. So here we are going to come across the word coherent and incoherent. Once again, I put it. Two sources of same frequency with phase difference remaining constant with time are said to be coherent. Okay, next comes like how to produce the coherent sources. How to produce the coherent sources. So I do have two light sources. Two light sources. Okay, let's assume that made up of same, manufactured by same company, same wattage, and they're identical. Can they be coherent? The answer is no. The two identical light sources can never be coherent. Anything, because what all the light energy that is emitted, it is due to excitation of atoms, and different atoms will have the different phase. So because of that, the two light sources can never be coherent. That's the basic condition. Okay, okay, we had a now discussion. Okay, let's proceed to the Huygens wave theory. It's a very beautiful concept and very difficult for students to really imagine. So I'll give some suitable examples. So it'll be very easy for you. Now this S is the primary source. Like it can be, what do you mean by primary source? Candle flame, a bulb, tungsten filament bulb, or nowadays we have modern LED bulbs. Okay, they'll emit light. Then how do that light wave will propagate? How do that light energy will propagate is what we are trying to understand here. How do that light energy in fact will propagate here? So here the Huygens what happened? He proposed like, so let's come to the wavefront. So this are you able to notice this like a 0, 1, I wrote one circle, 0. So there's a one wavefront of 0 phase. Next, a dotted circle is the red color. So there's a wavefront of phase angle pi radian. Next, a wavefront of phase angle 2 pi, wavefront of phase angle 3 pi, 4 pi, and the wavefront of phase angle 5 pi, and there's a wavefront of phase angle. So it will be 6 pi, and this will be 7 pi. So this particular source open, it will start emitting the waves. And we do assume here the idea of the wavefront. Sir, why don't you bring 0 to pi by 2, pi by 2 wavefront? Yes, you can bring pi by 2, 3 pi by 2. Let's assume few some specific things. So here, like there's a wave, the phase angle 0. As it propagates, it will acquire phase. Means you know that one. As the wave propagates a distance lambda, it will acquire a phase of 2 pi radian. So like that, what happened? We can define the wavelength also here. So what can be the wavelength lambda? Now distance between 0 and 2 pi wavefront will become lambda. Distance between 0 and pi will become lambda by 2. So we can take the wavefront concept here. No. So what Huygens is telling, every point on the wavefront acts as the source of secondary wavelets that spread out in the forward direction with the same speed as the wave. The new wavefront is found by constructing the surface tangent to the secondary wavelets. What is this? This is the point source. So what you mean to select it? Let me assume some 2 points on a wavefront of phase angle 4 pi. In turn, what happened? These 2 points, what happened? Every point on this wavefront will act like a secondary source. S is the primary source. S1, S2 open will become primary source. In turn, they also start emitting the wavefronts. They also start emitting wavefront. Next question comes, how do the wave will propagate? Direction to perpendicular, the direction of wave propagation will be perpendicular to wavefront. So what makes the light to propagate? What is telling is like, again, a point on a wavefront will behave like a secondary source and it will start emitting its secondary wavelets. Source of secondary wavelets. So what are secondary? The green color circles, what you can see there, the secondary wavefronts or wavelets. Then similarly S2. Okay, it will also start emitting. Then sir, how come it will move forward? Here the superposition of the fresh incoming wave and the waves emitted by the S1 superposition occurs and the energy will get added up and it will move forward. What about here? The fresh incoming wave and this one will undergo superposition and the energy, what happen here? Destructive interference will occur and the energy will cancel. So in this will happen, there'll be net flow of energy in the radial outward direction. The light wave propagates in radial outward direction. Means now, so let me assume S3, S4. What are S3, S4? Again, they will act like a secondary source. because there are points on the wavefront. So they will start producing their own wavefronts. So just imagine like every point on a wavefront or the pen will behave like a secondary source. And in turn, they'll start producing their own waves. So in this way, what happen? The wave will propagate is what the Huygens proposed here. Means, sir, what about S5? S5 is also a point. So like this, how many points I should assume? N number of points and the N number of sources are formed and they will generate their own waves and the waves, what happen, will start propagating. Okay, this was the Huygens proposed here. Okay, let's take the next one. Like a better diagram is what I'm trying to bring. If S is the primary source, this S is the primary source, so which will start emitting the wavelength. Okay, got the idea now. So A1, B1 is one wavelength. A2, B2 is the second wavelength. A3, B3, also like A1, B1 is one wavelength. AB is one wavelength. A2, B2 is one wavelength. Now, a point on a wavefront will be like a secondary source. So again, 1, 2, 3, 4 points I'm choosing. In turn, what happens? They will be like a secondary source. They will start giving out their own waves. They'll start giving out their own wavelets. Able to see this one? They'll start giving out their own wavelets. Then, so in this way, what will happen? Now I'll draw a tangent. I'll draw a tangent here. So tangent connecting that particular the wavelets. So again, what happens? That will become like a new wavelength. Or you can see this one like they're 0.1, 0.2, 0.3. So they're the plane wavefront. Every point on a wavefront will be like a secondary source. In turn, they'll start giving out the wavelets. Okay, now if I draw a tangent to that secondary wavelets, so I'll get the new wavefront. And that will be a plane wavefront here. So in this way, every point on a wavefront will behave like a secondary source. In turn, they'll start generating their secondary waves, and the secondary wavelets are formed. If you draw a tangent to the secondary wavelets, that will become a new wavefront formed by the secondary sources. So means now, sir, like what is the thing like, sir, like how come wave will reach here? So definitely what I can say different. So can you assume like this? And again, you draw a tangent. So this will become a new wavefront. In this way, what happen? Every point on a wavefront will be like a secondary source. So now what is the phase of all these points, 1, 2, 3? Suppose it is having a phase 3 pi, 4 pi, 5 pi. What is the phase of all points, like all these 4 points, 1, 2, 3, 4 on this wavefront AB will be 4 pi. Okay, are they coherent? No, I'm asking 1, 2, are they coherent? Yes, they are coherent. 1, 2, 3, 4. All these 4 sources at this instant, they are coherent because what is the frequency of the waves generated by that F? What is the phase difference between them? Will be 0. So 2 points on a given wavefront, will they be coherent? Yes, they'll be like a coherent sources. Okay, let's go back to again the Huygens wave theory. I think you can see things a little bit clearly here. Let me adjust it. Yeah. Now look at this one. There is a primary source which will emit the waves. Then the wavefronts are formed. Now S1, S2, are they coherent? What is the phase difference? What is the phase of this wavefront? 4 pi. What is the phase difference between S1 and S2? Will be 0. So at any instant of time, S1, S2 will become coherent sources. Then again, after this, will S2 and S3 will be coherent? Yes, it will be. S2 and S3 will be coherent sources. S3, S4, they'll be coherent sources. Now, S2 and S5, what is the phase of the S5? 6 pi. What is the phase of S2? 4 pi. What is the phase difference between 2 pi? And that phase difference at any instant of time will remain constant. So again, S2, S1 will be coherent. So that's why I wrote here, S1, S2. Are they coherent? Yes, in fact, they are coherent. So S1, S2 are coherent, S3, S4 coherent, S3 and S5 are coherent here. So not only 2 points on a given wavefront are coherent, will they, they become coherent sources. 2 points on different wavefronts will also become a coherent source. This is what I'm going to use in the coming YDSC setup. Very good numericals are related to this one. So let me summarize what do you mean by Huygens wave theory. So what Huygens wave theory says, like every point on a wavefront acts as a, I have that particular statement. Every point on the wavefront acts as a source of secondary wavelet that spread out in the forward direction with the same speed as the wave. The new wavefront is found by constructing surface tangent to the secondary wavelets. Means now I found a new wavefront. So what I should do? I should draw a tangent to the secondary wavelets here. So that will become a new wavefront. Got the idea now? So in a brief, in a sweetly, what I can say, every point on a wavefront of a primary source will behave like a secondary source. And in turn, they'll start emitting the wavelets. And if you draw a tangent to the secondary wavelets, that will become a new wavefront. This is what the particular Huygens principle is what is suggesting. Okay, now, when he proposed this, nobody could not understand because the rectilinear propagation was very simple and it was very mathematically, it was much easier. Later on in the YDAC setup after Young's double slit experiment, what happened there, the people started accepting it. Till then, what happened? The rectilinear propagation of light is what the ruled, the ray, the optics. Only after YDAC experimental demonstration, what happened? The people started accepting it. But both proposed the ideas at the same period. 14, like a 15, 1675, the Newton's, it's like a rectilinear propagation of light, and 1678 is the Huygens wave theory. But this was given recognition after YDAC set up in the 1840s. I think almost we can say 150 years. What happened after this? It was recognized. Okay, it happens in science because things are so complicated. So maybe the people found a little bit very difficult to assume this secondary wavelets, how the wave propagates everything. Okay, now how to, like how Young's was able to demonstrate this. Okay, let's do one thing. We'll go for the YDSC setup. Huh? YDSC setup. So let me bring the pen. Okay, we'll discuss the basic idea of the interference. What is the interference? So it's like an interference of light